So in the last hour, we found that we can write the integral of an equivariant form. That integral, is only over the complement of open balls. Okay. So today, now I'm going to talk about a specific localization formula. So it's Attila Bott, Berlin, Vernier. Okay. And their formula is for a torus action, but we'll just do it for a circle action. Okay. Now, in the last lecture, what we found was that if you integrate an equivariant closed form over the complement of open balls, you can write that as a finite sum over the fixed point sets. Okay. This idea can be used to prove other kinds of fixed point theorems. Okay. So whatever you want to integrate, if you can write it as an exact form, then you can do the same thing. So you get all kinds of great theorems this way. But what we really want is the integral over m. Okay? But what you can do is you can just take the limit as epsilon goes to 0. So as epsilon goes to 0, these balls, they become smaller and smaller. Okay? So their contribution to the integral will become negligible. Like in the limit, these are just points. And the integral on a point is 0. So when you take the limit as epsilon goes to 0, you'll get the integral of phi over m. That's what you want. And that will be a sum over the fixed point sets. Okay? And so you just have to work out what these numbers are. Then you have your formula. And they work it out. Okay, so, and this is their formula. Now, just a minute. So, at a fixed point, we have some data. So, an isolated fixed point P. So the tangent space is a representation of the circle. So it's a direct sum of irreducible representations, and we know that there are no trivial sum-ins. So the tangent space is a direct sum of n two-dimensional representations, okay? Because the irreducible representations of a circle are either one-dimensional, which are trivial, or two-dimensional, okay, which are kind of powers of the standard representation. And so these numbers are called the exponents. Exponents of the fixed point. Now, they're only defined up to sign because, Lm is equivalent to L minus m, okay? So, However, since M is oriented, so the tangent space has an orientation. Okay? And the L has an orientation because L is the two-dimensional representation, and it is the counterclockwise one. Okay? So the direct sum has an orientation. And you can say, okay, I will use only the positive exponents. But if you do that, now you get an orientation on the right-hand side, but there's an orientation on the left-hand side, and they may not agree, you know. Well, one way is like in the formula, you can put in a sign, a minus sign, if they don't agree. Okay? But another way is to say that we define the exponents up to sign. However, you want the two orientations on the two sides to agree. Okay? So the numbers are the exponents over here, defined up to sign, but with the requirement that the orientations on the two sides agree. Okay? So in other words, if you use all positive exponents and you find that the orientations don't agree, then you have to change one of the exponents to negative. Okay? And that's how you define the exponents at the fixed points. Okay? And then, okay. So, okay, so then this is their formula. And this formula was discovered by Atia and Ba in around 1982, but they published it in 1984. And Berlin and Werner published it in 1982. Okay? But they're independent proofs and of the same formula around the same time. Now, are you born before or after 1984? Most of you. 84, that would be 30-something. You're less than 30 years old, right? So, yeah, so okay, so it's before your birth, before your time. Yeah. But I was already a professor then. So it says if S1, but these, so you know, it's fairly recent. If S1 acts on a compact oriented manifold M with of dimension 2n, okay, with only isolated fixed points, and phi is an equivariant form of degree 2n. So it looks like this. And then the last term will be some function times u to the n. So this is an equivariant form of degree 2n. then okay, the integral of phi, well, it's going to be just the integral of 2n, because all the other integrals will be 0. Okay? And this will be a sum over the fixed point sets. Yeah, so it has isolated fixed point, let's say isolated fixed point set F. Okay? And these numbers, they calculated them and they found that it's just F at P over the product of the exponents. Okay. Yeah. And so here, the sign is very important, right? When you are calculating an integral, you have to have the correct sign for each term. Otherwise, you'll get the wrong answer. Okay, so let's do an example to see how this formula works. Example. So the surface area of, say, a unit sphere. If you can calculate the surface area of a sphere, unit sphere, then you can calculate the surface area of a sphere of any radius, right? Just by multiplying by r to the dimension. So
Do you need to assume that phi is closed or not?
Oh, yeah. I need to assume that phi is, yeah, that's right. And phi is equivariantly closed, right. Because, well, only for equivariant closed form can we get that localization formula, right? So, and so what is your question?
Because if you have no relation in pi 2 and f, the formula must not be equal. So this is my question.
Huh?
Because your phi is lying in omega s1 of u, polynomial of coincident pi.
Yeah.
So under this the following formula is that there must be relation of pi 2 and f.
Phi to n?
And f, the function f.
Oh, yeah.
So then there must be some relation.
That's right. And it comes from the fact that phi is equivariantly closed. That's right, yeah. So, yes, that's a very good point, yeah. So, you see, what is the condition for phi to be equivariantly closed? Maybe we should look at that first. What happened to my eraser? Oh, it's over here. Yes. So let's. Yeah. So the question is, what is the relation between phi 2n and f? Okay. Now, for a form phi to be equivariantly closed, that means dx phi is 0. So dx phi is d phi minus u ix phi. This has to be 0. Okay? And then, so what that says is that, okay, if you take d, let me see, yeah. So then d phi of 2n, now, let's see, so you take d of every term, right, yeah. Now remember, d of u is 0. Yeah, you see, so d of phi 2n is going to have degree 2n plus 1, but there will be no other terms of that degree. See, that's the highest degree. There's no other term of that degree. So this has to be 0.
It automatically, because that's the top form.
Yeah, it's the top one. And the other ones will never have that degree, right? 2n plus 1. Okay. And then you look at d of this. Okay. So d of phi of 2n minus 2, that has degree 2n minus 1. Yeah, so you have this term. Yeah, but you also have ix of this. Okay, so yeah, and that's multiplied by u. So let's put this. No, maybe I'll just let's just write it out. So dx phi will be d phi of 2n. Okay. And then and then d phi of 2m minus 2 u plus d phi of 2m minus 4 u squared, and so on. Okay, so that's the d part. And then minus u ix phi of 2n minus so ix of this, but again ix of u is 0, so just ix phi of 2m minus 2. Here's phi u, and then I multiply it by u, so I get a u squared. Okay. Let's write down another term. d of phi of 2n minus 6 u cubed, and then there'll be a minus, the next one is ix phi of 2n minus 4 u cubed. Okay, so this is dx phi. And so that's equal to 0 if and only if a polynomial is 0, if and only if all its coefficients are 0. So this has to be 0, and then d phi of 2n minus 2 has to be equal to ix phi of 2n. Okay. These have degree 2n minus 1, and then d phi of 2n minus 4 has to be ix phi of 2n minus 2. Okay. So, yeah, so these are conditions. And so there's a last one that says VF has to be IX phi of 2. Okay, so this chain of equalities relate phi of 2n to F. Okay? Yeah. You first start with the closed form, and then when you do take Ix of that closed form, it has to be D of something. So you find this one. And then you take the Ix of that one, you find the next one, and so on. Yeah. So eventually you find your F. Okay? Yeah. Yeah. So, let's just do an example, and then we'll see how it works. So let's compute the surface area of a unit sphere S2. Now we need an action of S1 on S2. We'll just take that standard action, the usual action. We rotate about the z-axis, okay? And then there are two fixed points, the North Pole and the South Pole. The S1 act on S2 by rotation about the z-axis. Okay. And the volume form on the sphere is omega is equal to, okay, do you remember the volume form on the sphere? It's, yeah, x dy wedge dz minus y dx wedge dz plus z dx wedge dy. Okay? And this volume form, we have checked that it's invariant because it's the derivative with respect to an element of the Lie algebra, say 2 pi I, and the Lie algebra S1 is 0. So it's an invariant form of degree 2. And the area of the sphere is the integral of omega. Okay. But instead of calculating this integral, I'm going to apply the localization formula. So I need an equivariantly closed form. Okay. And this omega is not equivariantly closed, right? Because I think we need an equivariantly closed form, omega tilde, that's going to be an equivariant extension of omega. So it's omega plus Fu. And the condition for this to be equivariantly closed is that, so d omega has to be 0, and then Ix omega has to be df. Okay? So dx omega tilde is 0 if and only if d omega is 0 and Ix omega is df. Now, this is automatically true because d omega has degree 3. Okay. And I think we worked this out before. What did we find f to be? Like ix omega is equal to d of 2 pi z. Okay. So yeah. So we found before that f is 2 pi z. Now, okay, now we have to find the exponents at the North Pole and the South Pole. Okay. Now, at the North Pole, if you look at the tangent space, well, you see that the action on the tangent space is just the usual rotation. So the exponent is 1 or minus 1. But just a minute. You have to make sure that the orientation, right, of the action on the tangent space agrees with the orientation of the sphere. Okay? So, I mean, from the picture, you see that it agrees because the orientation of the sphere using the outward normal is this. So, yeah, so it's 1. Now we orient S2 using, you can orient a sphere using the volume form, using omega. Okay? So in the sense that if V1, V2 is a positive basis, if it gives you the orientation for the tangent space, then omega evaluated at V1, V2 should be positive. Okay? And so the orientation of S2 at the North Pole is, at the North Pole, x and y are 0, so it's just dx wedge dy. Hence, a positive, so the orientation for the tangent space at P is ddx ddy. Okay? So you're going from x to y. That's the orientation. And yeah, that's also the orientation of, that's also, yeah, so hence the tangent space orientation is just L, because it goes from dx to dy. So the exponents at P is 1. Okay, and now let's look at, I'm going to leave the formula there. Let's look at the south pole. The omega at Q is equal to, now at Q is 0, 0, minus 1. So omega at Q, right, is minus dx wedge dy. And so the tangent space at Q is oriented by not dx dy, but dy dx, dy ddx. Because that's the one that's going to give you a positive number when you evaluate using omega. So what is the exponent at Q? It's going to be minus 1 because the tangent space representation, because your rotation is this way, like this, right? It's always, your rotation is from dx to dy, but the orientation of the sphere at that point is dy ddx. So hence m at Q is minus 1. Okay? And then by the ABBV formula, okay, so the integral of omega on S2, that's the area of S2, it's the same as the integral of omega tilde, because the integral of f is 0. And this is an equivariantly closed form. So it's going to be the sum of f of p over the exponent at p plus f of q over the exponent at q. Okay? And f of p, f is 2 pi z. Okay? Yeah, we found that f is 2 pi z. So at p, it's going to be 2 pi times 1 over the exponent 1. And at q, it's 2 pi times minus 1 over the exponent minus 1. Okay? So you get 4 pi. Yeah. For the area of the sphere. Yeah, so you see the advantage of this formula is that you actually don't have to do any integration. And you can calculate your integral this way. You know, and this is very useful because most of the integrals we want to calculate in real life have some symmetry, so it will be invariant. Most of the integrals you want to calculate are invariant. And so it will have an equivariantly closed extension. You know, yeah, you have to find an action with isolated fixed points. And then you can calculate the integral this way. Okay?
Is it possible to calculate the surface area or higher dimensional sphere by a similar method?
Yeah. Yes. 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 Now, but the reason why it's so easy is that actually all the calculations are done in the proofs. So in the proofs, you have to calculate the, it turns out you have to calculate the surface area of a sphere, okay? Because we reduce this integral to integrals over spheres. Yeah. So you actually, that's where the hard work is. You calculate the surface area of the sphere.
That's why I sort of remember calculating the area of high-dimensional sphere is kind of difficult, so that's why I'm asking this.
Yeah, but we have to do that first in order to prove this formula. But then once you've done that, then it becomes easy to calculate integrals because basically you reduce integrals to integrals over spheres. Yeah.
In general, is it easy to find omega tilde if given omega?
You have to solve that sequence of equations.
Yeah, is it easy or?
Let me see. So you have to solve so you have to start with a closed form, right? And then you do Ix omega 2n. That's easy.
Yeah.
And then you have to find the next one. So in fact, this is also a sequence of integrals, right? Because d of this is equal to this. So you're solving, it's a very simple differential equation that you can solve by integration. Yeah. So there is some work in finding this f. It involves some integration too. But I don't know, in the examples that I ask you to do, it's easy. I think I asked you to do one example, right? Is it on S2 cross S2? I forget, but yeah. There, it's easy to solve this. Yeah. Okay, so let's see. Let's. So let's try to prove the formula. Now, the thing is that we have to integrate on a small sphere that depends on epsilon, and then you let epsilon go to 0. So there could be a lot of terms, Now, there's a trick to deal with that, see. So now instead of integrating over a sphere of radius epsilon and then letting epsilon go to 0, okay, I can first blow up the manifold at a point, okay? And this is a way to avoid taking limits. Okay. Now, what's a blow up? The blow up is a map. Okay, the blow up of M at a point is another manifold M tilde, okay, so that the inverse image of P is a sphere. If I have a two-dimensional manifold, the inverse image is just a circle. Okay, and this map sigma is a diffeomorphism outside the circle in P. Okay? So basically, yeah, it maps this circle to the single point P. Okay, and M tilde is a manifold with boundary. This is M tilde, and okay. So that's called a blow up. The blow up of a manifold M at a point P in M is this manifold with boundary. M tilde is a manifold with boundary, and this map, when you take away the boundary, you get a diffeomorphism. Okay. And sigma inverse of P is the boundary, and it is in one-to-one correspondence with the unisphere in the tangent space of M. Okay. So you can think of it as like you replace this point by all the directions, all the tangent directions at that point. Yeah. So now there's always a blow up. You can just see. I mean, let's say try to do it in R2. So let B be an open subset of R2. Okay. So I define B tilde to be XV in B cross S2n minus 1. Okay. So be an open subset of R2 with well, let's say 0 in B. And, this is just S1. Okay. So S1 gives me all the different directions. So one of them is V. and I basically look at all the vectors in along that direction. So x is in the ray v, in the ray of v. So look at that set. Okay. And then define sigma from b tilde to b. Now, what is the inverse image of the origin? Sigma takes xv to x. Now, you see, because zero is in all the rays, right? Zero is in all the rays. So 0v is in this set. Yeah. I mean, if sigma xv is x, then the point has to start with 0, right? It's this, 0v. And for all v. They are all in that set. Okay? So the inverse image of 0 is S1. Okay? Now, what is the inverse image of a point x where x is not 0? If x is not 0, to be in v tilde, this v has to be a ray that contains x. If x is not 0, then there's only one ray that contains x, and v has to be x over the magnitude of x, right? Because it has unit length. So it's a single point. Yeah. So this sigma, it has an inverse. This is the inverse. Sigma is a diffeomorphism on b tilde minus that circle. Okay? Yeah. And it maps S1 to 0. So this is the blow up. Yeah. Okay, I'm going to stop here. Okay, a little bit over. Yeah. Now, if you can blow up at a point, then you see, if you have a manifold, you just take an open neighborhood and blow up that point, and nothing else outside will change. Only this point will be replaced by a sphere. Okay? So you can always blow up a point on a manifold. Yeah. Now, in the Soviet Union, this is a very standard process in algebraic geometry. So Shafarevich wrote a book called Basic Algebraic Geometry. It's a very good book. Have you seen it on algebraic geometry? But he in that book he talks about blowing up. But in Russia it's very dangerous to talk about blowing up something. You see, because they might think that you are trying to blow up a bridge or a building. So in that book, the blow up is called the sigma process. Yeah. Yeah, but in the United States, we all talk about blow-ups all the time. Yeah. And when that book was translated into English, in the first edition, the translator kept the Russian terminology, so he called it the Sigma process. Yeah, but in the second edition, he felt comfortable enough to call it the blow-up. Yeah. Okay, so see you next.